This video is just going to do a few more examples, only 3. It's short, and those examples are going to be with more integration. So the first thing to know is that when you do examples like this, which go from -4 to 4 or kind of center around some sort of origin, then if I have an integral like this, I can use even-odd analysis to tell what this is pretty quickly. And if you're going to do that, you need to have some sort of proof of why you decide that the function is even or odd. To review this for the 7,000th time, and if I would have told you I'm reviewing it for the 7,000th time, Mrs. Manton would get really upset with you. Even functions are if f of negative x is equal to f of x. And so those are things like absolute value. Those are functions like cosine. Those are things like even powers. And we have even powers over here. So we can probably hypothesize that it's going to be even. Odd are if f of negative x is equal to negative f of x. So I could do things like odd powers. We have trig functions that are odd. Specifically, you have sine and cosine, or sorry, sine and tangent that always output whatever the sign is that you inputted, or the opposite of the sign that you input. Or if you input a negative, you get a negative. You know what I mean? So those are odd functions. Now, this, if I establish that it's even, I can think of this as a couple of things. I can't immediately decide that this is 0. Don't jump and say that because this is even it's 0. That doesn't make sense. But what I do know is that since it's even, I can say that this is equal to 2 times the integral from 0 to 4 of x to the 6th, x to the 6 minus 2. So if that kind of can simplify things a little bit, because if I'm just going to do 2 times the integral from 0 to 4 of x to the 12th minus 2x to the 6th dx, and then integrate that, I only have to worry about the plugging the 4 in and then just multiplying the result by 2. So this would be x to the 13th over 13 minus 2x to the 7th over 7 from 0 to 4, and I would get 2 times 4 to the 13th over 13 minus 2 times 4 to the 7th over 7. And I don't have to worry about the minus 0 part because it's a polynomial and everything has, an x value in it. The only simplification I would kind of do with this is change those 2's to 2 to the 26th over 13 minus, this would be 2 times 2 to the, so 2 squared, so that should be 2 to the 15th over 7. And I feasibly could just multiply that 2 back in and make it 2 to the 27th over 13 minus 2 to the 16th over 7. So that would give you kind of a version of an answer that you might see in a multiple choice on an AP exam, or you might just have to verify using a calculator that it's equal to something. You really won't see 2 to the 27th though. Second example, I've got an integral from negative pi over 4 to pi over 4 of 2 sine x cosine x dx. So you could do an even-odd analysis on this. You could say f of negative x is equal to 2 times the sine of negative x times the cosine of negative x, and then pull the negative out of the sine and know that that's negative 2 sine x. Cosine of negative x is just cosine of x, so I know that f of negative x is equal to negative f of x. Therefore, this thing is odd. But if you also recognize your identities, you know that 2 sine x cosine x is the same as saying the sine of 2x. And the sine of 2x, because its sine, is going to be an odd function anyway. Anyway, given that this is an odd function and I'm centered around odd means origin symmetry, I know that negative pi over 4 to pi over 4 is just going to be 0. So that's enough to do that. And I know that because the integral from 0 to pi over 4 is the opposite of the integral from negative pi over 4 to 0. So when I bring them together, I just get 0. We've seen that a few times. Finally, we have tricky ones, and this is just kind of one more example of one that I really can't use a heavy even-odd analysis of. So I have 2 pi over 3, negative pi over 3 to 2 pi over 3 of the tangent cubed x dx. So the only thing that odd symmetry is going to let me do with this, because I know that tangent is odd, is basically wipe out everything from negative pi over 3 to pi over 3. If I separate this into negative pi over 3 integrated to pi over 3 of tangent cubed x dx, and I add the integral from pi over 3 to 2 pi over 3 to just kind of make every line equal to the one that came before. I know that this is going to be 0 because that's just negative pi over 3 to pi over 3, but I still run into this problem of what's the integral of tangent cubed. So that's what I want to kind of talk about now. The best way to do this, because I know that this is the same thing as the integral from pi over 3 to 2 pi over 3 of the tangent x cubed dx, if I let u equal tangent, I don't really get anything. So that's not going to work necessarily for this. I want to keep it kind of as the tangent cubed. But I do want to separate this and remember kind of an identity we know about tangent. So if you're forgetting your identities, you know that sine squared x plus cosine squared x is equal to 1. And if I divide both sides by cosine, I get tangent squared x plus 1 is equal to secant squared x. Then if I solve for tangent squared, I get tangent squared x is equal to secant squared x minus 1. That can substitute in for tangent squared, and this entire integral can become the integral from pi over 3 to 2 pi over 3 of the tangent of x times tangent squared, which is secant squared x minus 1 dx. That is useful not because I can let u be, if I let u equal secant squared, that doesn't really help. If I let u equal tangent, I get secant squared, but this isn't secant squared, it's secant squared minus 1. But I can use the distributive property and make this the integral from pi over 3 to 2 pi over 3 of the tangent of x secant squared x minus, this would just be the integral of pi over 3 to 2 pi over 3 of the tangent of x dx. So in this case, I would let u equal the secant of x, and then du would be equal to the tangent, my bad, flip it around, du is equal to tangent x, du is the secant squared of x dx, so dx is equal to du over secant squared x. Substituting in and doing my substitution, so I'm kind of going back to drawing triangles because it's been a while since we've done the trig, so this is going to be my pi over 3 and 1, 2, root 3. So if I'm changing my limits on that one, let me make sure I have my, I don't have my dx right here. Now I've got it. If I'm changing my limits, let me keep this whole screen on, just flip colors. I'm going to get the integral from the tangent of pi over 3 is root 3. Then the tangent of 2 pi over 3 is, let's see, would be negative root 3. So root 3 to negative root 3. Because 2 pi over 3 is the same thing, but in quadrant 2, of u. And the secant squared cancel, so just u du. And that's going to be minus. Then I'm just going to do an integral of tangent, which is a little, hang on just 1 second. Okay, back to this. The best way to do the integral of tangent is actually just to split it into sine over cosine. So I'm going to keep this going and just make this sine x over cosine x dx. I'm going to call it a v substitution. So we're going to let, I want to cancel sine out. We're going to go v is equal to cosine x. So dv is equal to negative sine x dx. And that means dx is equal to dv over negative sine x. The negatives are going to cancel. The signs are going to cancel. I'm going to go ahead and do this integration right here. So this is going to be u squared over 2 from root 3 to negative root 3. And that's going to be plus the integral from pi over 3 to 2 pi over 3. Oh, sorry, let's change our limits. Plug in for cosine. Cosine of pi over 3 is 1/2. Cosine of negative, or 2 pi over 3 is negative 1/2. And that's going to give me, let's see, we do the replacements. I get 1 over v dv. So this is going to give me 0. You should see why with the square. Plus, the integral of 1 over v is one we talked about. It's the ln of v. And that's going to be from 1/2 to negative 1/2. We talked about it with an absolute value. So then I get 0 plus the ln of negative 1/2, absolute value of negative 1/2, minus the ln of absolute value of 1/2. and that gets me 0. And we are done.